tutorial about equality types, and in particular implementing the equality types in Dhall. Dhall is a language that implements system f omega, which can be seen as lambda calculus with higher kind types. And it is a subject of my recent book that I'm following in this tutorial. So let me begin by saying what is the equality type. Now, equality types are a feature that is usually available only in dependently typed languages, and Dhall has this type because it does have some dependently typed features beyond what system f omega in principle should have. So let me explain, because programmers usually don't have these types in their programming languages. So what is an equality type? It's a type that is denoted like this in Dhall. It's a type that is parameterized by two values, and for each pair of these values it's a different type. So let me show you what that is. So it's a type. You see, it's not an expression with value, it's a type. So there can be values of this type. And for each pair of numbers, there's going to be a different equality type. And so different values of all those types. Now, actually, these types are very simple as types. An equality type is either void, it has no values, when the two parameters are different. So for example, 1 equals 2 is a type that has no values. It's void, as one says in type theory, or uninhabited, as one says in type theory. It has no values. And if the two parameters are the same, say 1, so let me say t12 is going to be this type 1 equal 2, and t33 is going to be the type 3 equals 3. So I have defined type t12 and type t33. Now t12 is a void type. There are no values of that type. But t33 is not void. It has a value. It actually has exactly one value, which in Dhall can be created. Let me do that. I'll call it from lowercase t33, and it will be a value of type t33, and the syntax in Dhall is like this: assert. I can say t33 here. Now it's not going to be very easy to read, so I will just write it out again. The type t33 is the same as 3 equals 3. It's just the same expression. So you see the value lowercase t33 has type capital T33. So I have a value of that type. Now, so actually there's only one value of that type, and it is this value. This is the syntax for that value in Dhall. And that is a typical situation. Equality types are defined as functions of two parameters, and if these two parameters are equal, then the equality type has a value, and that value is only one value. In type theory, that value is usually denoted by the symbol reflexivity, because the property that some value is equal to itself, that property is called reflexivity law of equality. And so in theories, in theoretical literature, that is what it is called, reflexivity. But this is just a name. The point here is we can have types that depend on values. So for each pair of parameters, we have a different type. And these types have values if the two parameters are equal. So this is how Dhall defines this for this syntax. I will not be able to write something like this, assert 1 equals 2. That is incorrect. Assertion failed. I failed to define a value of this type. I can define a value of type 10 equals 10. That's fine. So that I can do. Note that this is value of a different type than this. So if I say let t10 equals this assert, then actually t10 is not of type t33. That is incorrect. So it's a different type. So it's not true that all these assertions are just somehow equal to true or something. No, they are all values of different types. So that is how equality types work. They're all different types. So 10 equals 10 is one type, 3 equals 3 is another type, 0 equals 0 is yet another type, and so on. So this is how equality types usually are defined and work. So why do you use them? You use them as evidence that two values are equal. So when you know that two values are equal, then you can create a value of that type. And if you have a function whose argument has this type, then you know that these two values are equal. So you can have a function, let's say, which you define like that, x natural, and then y natural, and then x equal y, and then I don't know, let's do something. So that is going to be the type of this function, and it's the body of this function is going to be lambda of x natural, lambda of y natural, and then lambda of evidence that x is equal to y. And then let's just return x to have this example. Now I have defined a function whose arguments have these difficult types. One of them is this. How do I call this function? Well, I can call this function like 1. Then I have to give actually, let's call it 3. Then I get an evidence, t33, that 3 is equal to 3. So I can call this function like this. Now I have defined t33 previously using this syntax. So t33 is a value of type 3 equals 3. And that's why it fits the type signature of this function. So this function has a dependent type signature. The type of one of its arguments depends on the value of the values of the previous arguments. So this is a dependently typed type signature of the function. And when I call this function, I need to provide two natural values and then an evidence that they are equal. Now, this is, of course, an artificial example, but that's an example to show how you would use equality types. So now let me go to Leibniz equality. If Dhall did not have the assert syntax and this triple equals syntax, it turns out you could still use Dhall to define exactly the same features by encoding them in a clever way. And this is the subject of this tutorial, how to encode equality types. And this encoding is called the Leibniz equality type. So this is the encoding. It has this type signature, which is that it depends on an arbitrary type and on two values of that type. And the result is the equality type for those two values. Now, of course, it is important that these two values have the same type. If they're not the same type, then it's a type error. and we want to keep it that way. So if I go back to my code, if I want to say 3 equals bool, that's actually not a type. That's a type error. I cannot have a type of this sort. I can have a type 3 equals 10. 3 is not equal to 10, but the type is well defined. That type will have no values because you will never be able to give evidence that 3 equals 10, but the type itself is well defined. But 3 equals bool is not well defined. It's not a type that we can define, and we want to keep it that way. So that's why I say we have to specify what type both these parameters will be, and then I specify these two parameters, and the result should be a type. So how do I encode this type? Well, I take the type T, I take A, I take B, and then I write this expression type, which is for all functions f that transform T into type, I need to be able to transform FA into FB. Now, what is FA? FA is a type, because f is a function from T to type. So FA is a type, FB is another type. And I should be able to transform from one type to another, not even knowing what those types are. How can I do that? Well, I can't, unless I know that A and B are the same, that are equal. If I know that A and B are equal, then this FA is the same type as FB. That is clear, because we are applying a function f to the same value, if A is equal to B. So if I know that A is equal to B, then I know that these are equal as types, and so I can implement an identity function from one type to the other, because they're the same type. That's how this works. Here's an example. Suppose I take natural as this type T. Then I have A natural, B natural, and then for any f from natural to type, I need to transform FA to FB. So how do I do that? Suppose I have 0 and 0 here. Then I need to have this sort of function. So can I implement that function? Yes. I take a value of type f0 and I return the same value. I don't know what that type is, but I can take a value of that type and return the same value. Even if that type is void, I can still write this function, because this function doesn't require me to have values of this type. If I have a value p of type f0, I can return p. That's all I know, and that's sufficient. So I have implemented a value of type Leibniz equality natural 0, 0. But I cannot implement a value of type Leibniz equality natural 0, 1, because then I would have to return a function of type f0 to f1. But f is an unknown function, so the types of f0 and f1 can be completely arbitrary, and we don't know what those types are. We cannot implement that function. Or maybe f0 could be a unit type, and f1 could be the void type, because such an f can be easily defined. This is such an f. And then if I apply this to 0, that will be a unit type. And if I apply this to 1, it will be a void type. Let me try that in the interpreter. So unit if 0, 0. That's a unit type, and that is a void type. That's how it works. And if we could have a value of this type, then we would apply that value to this function and to a unit value, and we would obtain a value of the void type, and that cannot be. That would be a contradiction in the type system, and so we cannot possibly write a value of this type. That is how Leibniz equality works. So it is a very clever type construction, and the reflexivity can be defined through it by just returning the value of this unknown type ft. So now we have seen how this works for the natural type. We can go back to arbitrary type t instead of natural, and now we can implement this value. So for any type t, we can implement a Leibniz equal tt by this code. And that is the REFL. In dependently typed languages, usually that's what is denoted by REFL. But of course, in independently typed languages, one doesn't encode anything using Leibniz equality. It's usually built in. And similarly in Dhall, it is built in as assert and the triple equals. But actually, it turns out that Leibniz equality is a little more powerful than Dhall's assert and triple equals. This extra power is not often necessary, but it is there. Let's take a look. So first, actually, let's see if we can use assert, if we can use Leibniz equality to implement assert. And we can, and this is going to be like that. So suppose we want to assert that 123 equals this expression. And that's how we would do that. We would say there is a value which is evidence of this equality, and that evidence is of type Leibniz equal, natural, 123, and this. Because it is of this type, the type checker checks and it checks, so then it is equal. And it is in Dhall written like this, using the assert syntax. So you can just see mechanically we replace the syntax. Instead of that, we write Leibniz equal natural this, and instead of assert, we say REFL natural blah. So it's much more verbose, and you have to repeat yourself, and you have to put the natural type in here explicitly in Dhall. But other than that, it is functionally the same. So in this way, you can reproduce the Dhall features using this construction. So you see, we defined this and this in Dhall using just some quantifiers. We didn't use the assert syntax or the triple equal syntax to define that. And yet, the effect is the same. We can actually go further. We can convert this into this directly. And here's the function that does that, to assert type. So if I have a type, a value of this type, then I can obtain a value of this type, regardless of x and y in general. It's a very nice illustration of how Leibniz equality works. How do we use that? Well, we need to take a value of this type and apply it to some function f from values t to types. What is that function going to be? It's going to take a value a, and it's going to return this type, which is built in Dhall. And how do you provide the equality? You provide it like this. So the value of this type you provide like that. This will type check only when x and y are equal. This will not type check when x and y are not equal. When you use this function. But this function is defined. It is well defined in general. You transform this into that. Well, if x and y are not equal, you will never be able to get values of this, and so you will never be able to apply this function to this kind of value. But the function you can write down in general. That is how it works. So then this syntax is exactly that. So in this way, we have completely reproduced the assert functionality. Now, another thing we can do is we can do inequality types. We can try to say the types are not equal. So how do we do that? Well, we can just say this type must be void. And to do that, we make a function from that type to void. And that function, if that function can be implemented, it means that this type is void. So how do we do that? Well, we can do this through the function I call Leibniz unequal, which is very similar to Leibniz equal, except it takes this and returns void type. So how can we do that? Well, what we do is, let's suppose we take an example, natural and 1 and 0. So 1 is not equal to 0. So we need to implement this Leibniz unequal natural 1, 0. How do we implement it? Well, we need to implement this sort of function. How do we implement, given this function k, we need to return void type. How do you do that? Well, you don't actually return values of the void type. You just write a function that would have returned those values if given its argument. It will never be able to get that argument because, as we know, this cannot be implemented. But we need to write code that type checks that if someone were to give us a value k of this type, then we would have returned the value of a void type. That's completely hypothetical, and that's the code we need to write. And in order to write this code, we apply this k to a function that returns the void type with 0 and the unit type with 1. Here's this function. If x is 0, then we return the void type, else we return the unit type. And then we apply this function, k, to this f. And then f1 is the unit type, so we give the unit argument. And the result is a value of type f0, which is void, as promised. So this type checks. Now, it's important here that we can do this because we can check that x is 0 or not at runtime. We would not be able to do that in Dhall if all we know is an equality type between x and 0, because we cannot write code using that. That equality type is not going to give us code that compares values at runtime. So Dhall has a limitation where you cannot do asserts at runtime. Asserts are done at compile time. So that means you cannot do inequality types in Dhall unless you can distinguish values of type t at runtime. So I have formulated it like this. You have to be able to distinguish values of type t via bool-valued functions or via merge expressions. Like this one. This is a bool-valued function that allows me to see if x is 0 or not at runtime. It is a stronger requirement than just saying that I have evidence that two values of type t are equal. And because Dhall does not support bool-valued functions to compare, say, text values or double values or other such types, it can only compare booleans, naturals, and integers at runtime. And so because of this, you cannot write code for that kind of thing. So ABC is not equal to DEF, but you cannot directly write a comparison at runtime, and so you cannot implement this inequality. So unless new features are added to Dhall, you would not be able to do that. And there are reasons not to add those features to Dhall. Although it might be that they will be added. So this is an interesting detail where we can have Leibniz equality even though we don't. So we can have Leibniz equality between text values, ABC, ABC, but Leibniz inequality is stronger in some way, and it requires more power from the language. But actually, there's an argument here saying that even if we add Dhall comparisons for text or double, it wouldn't help us necessarily for other cases, like functions, because it is not possible to compare functions at runtime. Dhall can compare functions at compile time by comparing their source code, and so in some cases this is sufficient, but in any case you cannot efficiently compare functions at runtime. And that is not possible for arbitrary types T. And so this shows that the Leibniz inequality type is in some sense a stronger thing than equality type. That's an interesting sort of intuition. Similarly to Leibniz equality at value level, we can do Leibniz equality at type level. A very similar thing. Dhall does not actually have asserts for types, so you cannot do this. This is not allowed in Dhall, and this is not allowed in Dhall. But you can define Leibniz equality at type level in the same way, very similarly, except that T now will be not a type, but kind. So this could be, so A is a value of type T, T is a kind, so let's say T could be type, A could be a value of type T, which is, say, natural, so A could be natural, and then you have a function from type to type here, and it does exactly the same thing, but at type level. And if you have a Leibniz equality at type level, which is an evidence value of this type, it means that P and Q are equal types. So you can convert values of type P into values of type Q. And here's a function that does this. All you do is you apply this evidence value to an identity function at type level. And so this is a typecast. So this kind of thing actually is more familiar to programmers, because equality of types at type level can be encoded in languages like Haskell and Scala through type classes. And that is more familiar, actually, the equality at type level. An evidence value, which shows how to convert one type into another. And that's exactly what it is here, but it is on a more general scale. So this, see, this is a kind. So this could be arbitrary kind in principle. And then we can do assert-like functionality for types. Again, this is a bit verbose, but it can be done. One of the principles that I think Dhall should follow is that if you can encode something in pure Dhall using some verbose encoding, then it is safe to add that using some kind of syntax sugar to the language. It will not change the power of the language. It will not break anything in the language. You just need to find suitable syntactic sugar so that using this feature becomes more natural and easier. But so this is an example. Dhall does not support such syntax for types, but you could implement exactly the same kind of syntax, exactly the same functionality, not more and not less than this. And so it will be just the same type checked at type checking time, not at runtime. You will not be able to examine types at runtime. Nothing changes really in how Dhall works. And because this is implemented in the unmodified Dhall language. And so because we can implement such a thing, there's nothing wrong in adding such syntax to Dhall. So this is an interesting principle in language design. You implement a small core language. You explore what can be implemented in that core language. And when you find some helpful and useful feature, you add that feature as a syntactic sugar to the language, knowing that it will not break anything, you will not introduce any hidden problems. The core language remains unchanged, and you can just desugar this under the hood into something like this, and the users don't have to look at it. What you can do further with Leibniz equality, something you cannot do with Dhall's assert syntax, is symbolic reasoning. So what do I mean by symbolic reasoning? If I am given evidence that x is equal to y, then it makes sense that also I should have evidence that y equals x, because equality is symmetric. So generally, there are different properties of the equality relation, which I listed here: reflexivity, symmetry, transitivity, value identity, and function extensionality. And I will go through that now to show how that works. Reflexivity is that any value equals itself, and so we should be able to get values of this type. And indeed we do. We have a combinator for that. The symmetry means that if I have a value of type equal xy, then we should also be able to get a value of type equal yx. And in the language of programming, it means I should have a function that transforms values of this type into values of that type. So a combinator, so to speak, for the Leibniz equality. So what is that combinator? It should have this type signature. And indeed, I can implement it. So the interesting thing that you have to do here is you need to reason with these dependent types. You're given this value, which has a difficult type signature. How do you create this out of it? Well, here is how. You have your function, x equals y. You need to apply it to arguments. But to what arguments do we apply? Well, one is this function from values to types, and the other is gx. So then you have to find how to define those functions. And here's the code for it. Here I motivate how that works. The only way to obtain the value that we want, which is this one, is by applying this to some arguments. Now x equals y is a higher order function. So we need to apply it to what arguments? The first argument, g, must have this type. And the second argument, h, must be this. And the result of this must have type gy, because of how Leibniz equality is defined. Is when you apply this to g, and the first argument is gx, and the second argument, the output value will be of type gy. So gy is going to be the output if you apply it to g and h. But what we want is this output type. So gy must be equal to this type. So we define g as a function that takes x and returns this type. That's how we define it. It takes, well, t and returns this type. And H is just REFL because H is of type GX, which is Leibniz equal XX. So that is going to be just REFL. And now we are ready to apply. So this is the way to figure out code of those combinators. You look at what arguments you need to put into the Leibniz equality and what output types you want. And then you figure out what the type functions must be. The transitivity property is that if you have a value of this type and a value of this type, so if x equals y and y equals z, you should be able to get a value of this type. So implementing this is similar. We need to figure out to what arguments to apply the given values. And I will skip that. I have written out in detail all this reasoning. So this is how you implement it. What is value identity? I call it the property that if f is any function and x equals y, then fx equals fy. So for any function f, if you apply any function f to equal arguments, you get equal values. And function extensionality is a similar property, but for two different functions. If functions are equal, it means you apply them to any argument and you get the same value. So this is kind of value identity, and that's function identity in some sense. So both of them can be implemented as combinators with Leibniz equality. So if I'm given that f is any function and there is a Leibniz equality between arguments, then I can derive Leibniz equality between values of that function applied to those arguments. And function extensionality is that if I'm given a Leibniz equality between functions, then I can apply these two functions to some x, any x I want, and I get a Leibniz equality between the results. And so I skip the derivation because it's all written here. It's very similar. You just need to figure out to which function to apply the Leibniz equality, and that is figured out by looking at the output type and seeing what is the required output type. So now I give you an example of symbolic reasoning. What is a symbolic reasoning? Well, we have it means that you're given some equality evidence values and you derive new equality evidence values in some way. So here's an example. Suppose I have an evidence that x equals y, and I have an evidence that f equals g. So f and g are some functions. Then I want to show that fx equals gy. So I need evidence value that fx equals gy. So how do I derive that? I derive that using different combinators that I already have: the extensional equality, identity, and transitivity. So this is kind of reasoning that I'm talking about. So it is similar to mathematical reasoning. I have extensional identity, so fx equals gx. Because f equals g, I have because f equals y, I have fx equals gy. So this, and then I have transitivity. So this is how this works. Note, however, that Dhall's assert does not allow us this kind of reasoning because there are no functions in Dhall that can consume values of this type and do anything with them. So for example, if I have a value x equals y, triple equals, I cannot derive from it a value of type y triple equals x. There's no functions defined in Dhall that can take this value and produce me a value of the other type. And also, I cannot convert this into the Leibniz equality value. But if I could, then it would be sufficient to do all of this. So a natural extension for Dhall would be to add a conversion function from the assert values to the Leibniz equality values. Because you can always convert back. I already implemented how to convert back. I showed you that. But to convert from assert to Leibniz equality is not possible currently in Dhall. And it should be, because Leibniz equality is just a more verbose way of encoding exactly the same thing. So I would argue there should be. So this is another example of this sort of reasoning. So if I have a function of 2 arguments and I have evidence that a equals b and c equals d, then FAC equals FBD for any function f. And so with Leibniz equality, I can do that by combining these 2 combinators. There are a lot of types and a lot of parameters that you have to write out. Other than that, it is very straightforward. So this concludes my tutorial about Leibniz equality.